contribution. And we turn to the last contribution from the first part of this afternoon. The paper is by Mr. Nassajian Moghadam Mohamadreza. He's a PhD studying Professor Dominique Pioletti from the EPFL in Lausanne. So welcome, and we look forward to your presentation. What is the title of your talk? Temporal control of drug release from self-heating hydrogels.
Thank you very much. I'm from Laboratory of Biomechanic Orthopedics from Lausanne. Sorry for my long name. You can call me Reza simply. And this is in collaboration with the Laboratory of Polymer. So, as you know, due to our active lifestyle, the risk of knee injury is very high. And when you have knee injury, you have a high chance to have focal defect in cartilage. The healing process, as you know, in cartilage is very limited, and there are groups of growth factors that have a significant impact in regeneration of this tissue. Also, cells secrete this kind of growth factor. It has been shown that the delivery of this growth factor for defected zone is our great interest. So what we propose is to have a control release system to deliver this growth factor to the site of effect with mechanical load. But why we need to control the release and why with mechanical load? As you know, the knee cartilage in knee is kind of open system. That's why we don't have like efficient drug delivery system, because every drug that you inject there, it goes away with synovial fluid immediately before cell can take it. So it's very important to have something controlled there. Mechanical loading improves the activation of TGF-beta growth factor. That means that when you have mechanical load, you have more receptor upregulated. This has been shown in literature. And interestingly, there is a delay between the when you apply mechanical load and when this receptor are upregulated, because there is cascade of event that it has been shown it's about 20 minutes to half an hour to respond to this mechanical load. So to have an efficient drug delivery system, it's good to have, in this case, a drug delivery that controls the release with mechanical load and provides such a delay between applying the load and release of the drug. What we propose here, we introduce a new variable. It's not new, but for drug delivery system, which is viscous dissipation. With this parameter, we can control the release of drug with mechanical load and, as I told, provide such a delay. But the system that we propose, it works that it consists of two components, a hydrogel system, which is very viscoelastic with low permeability. And inside this hydrogel, we have some thermosensitive nanoparticles that they are designed to shrink when the temperature reach to their critical temperature. So imagine that you apply load on this system. When you apply load, as I told, the hydrogel is very viscoelastic. So when you apply load on viscoelastic material, they dissipate part of energy, which is heat, actually. And if you continue loading, cyclic loading for specific times, you can, playing with viscoelastic properties of this material, you can regulate this time to be from several minutes to half an hour, for example, what I need. And at each loading cycle, the material can heat up a bit. That's why we call this material self-heating, because it dissipates lots of energy. And after a certain number of cycles, the temperature reaches to the temperature that we need for nanoparticles. At this point, the nanoparticles shrink, and when they shrink, they occupy less space and increase the permeability of the gel. And consequently, you have much more drug release. So in this case, we have mechanical load. We control our release with mechanical load, but we provide a delay with playing with viscoelastic material of this hydrogel, and then the drug can be released. To design such a system for hydrogel is very challenging. As you know, hydrogel, they are very soft material with very poor mechanical properties. So what we need is to have a hydrogel with high dissipative properties and high mechanical toughness. Means that in load-bearing application, they shouldn't be ruined when you use them. studying different hydrogel structure, we found that HEMA-based hydrogels, hydroxyethyl methacrylate hydrogel, they have good properties that when you use them with very small crosslinker, short-length crosslinker like HDMA, they can produce lots of friction inside material when you apply load, and they dissipate lots of energy. As you know, this doesn't work. The hysteresis curve, which is like identity for dissipation under load, for this hydrogel, when you use very short crosslinker, is much higher than when you use long crosslinker. And the dissipation is good thing because it's in the favor of mechanical toughness of the gel. When you have the gel with high dissipation, it dissipates the input work and doesn't let that the energy is stored in material to lead to crack. We played with different parameters in this hydrogel, like crosslinkers and water ratio, and we could reach to wide range of mechanical properties. On the other hand, we had these thermosensitive nanoparticles, which were produced by room temperature inverse mini emulsion of isopropyl acrylamide, and they are designed to have very sharp response at 37 degrees. So when the temperature change from 36 to 37, they shrink from, and their size become from 340 nanometers to 240, means that they become, in volume, they become almost half size. And we produced our smart hydrogel with selecting the right hydrogel, and then mixing with nanoparticles, and with UV polymerization we could produce. And we used, like, for proof of concept, we used like a model drug, which was like a silencianol, not real drug in this case, to have no interaction. And first we started the passive release of hydrogel, so we had two groups without nanoparticles and with nanoparticles, and we incubated them at 34 and 39 because the response temperature for nanoparticle was 37, so below and above. And then we found that with the group with nanoparticles, which were incubated at 39, we had much more release comparing to other, means that they are, the thermosensitivity of the nanoparticle works even without mechanical load. And the diffusion coefficient that we measured experimentally from this, for this hydrogel, showed that the hydrogel are about three times more permeable at 39 degree comparing to 34. Then we characterize drug release under load. For this, you need a system that to be heat isolated, because the temperature that we produce under load, we didn't want to go away, so we should reserve it somehow. So I designed a system with two-layer wall with the vacuum in between, that you can control the heat loss of the system, with the chamber around that with water perfusion, that you can control the temperature of environment. And when you apply load on this material, and when you set the environment temperature at 36, for example, after 5 minutes, in this case, loading, the temperature can increase 1 degree and reach to 37, which is required for nanoparticles. And again, we had our 4 group. Once we set the environment temperature at 34, we didn't have a significant difference between the 2 groups, because when you set at 34 with loading, it never reached to 37 with this system. But when we had at 36, after loading, 5 minutes loading in this case, we had much more release from the group of with nanoparticles comparing to without nanoparticles. That it shows that here we could show the proof of concept of the figure that I showed first. So we control kind of release with mechanical load, and we provide the delay here 5 minutes, but you can, as I told, play with this delay to increase it. And the interesting thing is that the release that you have here comparing to passive release is much higher, and this is due to kind of hydrophobic properties that our gel has, that they don't have lots of passive release. So it's more the release under mechanical load, not because the idea was to have mechanical load for release in favoring the receptor of the drug. But now we published the first part, and now we should move to the real application. The first challenge was the biodegradability of the gel, because the system that we showed by now, it was for proof of concept, and it wasn't degradable. And for the degradation, still it was a big challenge again because the biodegradable gel, they are very soft because normally they are natural cross-linker. And for that, we needed to find the cross-linker that exactly have this properties of HDMA that we used. And we also had concern about the degradation product because in this case, it will be very long hema chain that maybe they cannot be absorbed in body. So I used the tetrafunctional molecule, which break kind of the lengths of hema. So your degradation product will be such a molecule like this, which is a very small molecule. And the degradation study now is under study still, but the first results showed that they had very good degradation comparing to other hema hydrogel that people introduced before. So this hydrogel, they are designed, the idea was that we didn't want to have interaction with drugs. So as you saw, we just played with the permeability of the gel in this case. So basically any kind of drug can be used in this system. We just need to set the size of the drugs with the permeability of the gel. And for example, one application that can be, it's like in mucoiplasty in knee cartilage when they move the plug of cartilage from non-load bearing side to the load bearing side. This kind of drug plugs can be used in between our cartilage plug to release growth factor required drug in this case and degrade after a while. And thank you for your attention.
Interesting and competent presentation. You did a very good job. Any questions, please? The people from the first row, Arul?
Can you say how your test drug is bound in your hydrogels and what mass ratio you can load it up to?
So as I told, the idea was that you have no interaction with drug. So what it keeps really the drug is the permeability of the gel. For example, these gels, they have like mesh size less than 2 nanometers, which it's all experimental measurement of the release. So they are basically not binded to the gel. They are free inside the hydrogel, but you don't have high passive release as I showed, because of the special properties of the gel that they have a degree of hydrophobicity that they are not very interested to release the drug when there is no force after them. Yeah.
Further questions? Peter Gehr, bitte.
I may have missed that. What nanoparticles did you use and what was the purpose? What's behind the nanoparticles in the gel?
So the gel, as I told, maybe I showed this slide again. This one. Mm-hmm. The gel, as I told, is it's really a gel with very low permeability. So if at normal temperature, you don't have a lot of release. But the nanoparticle that we used, the idea was that when the temperature reached to, for example, 37, they shrink suddenly. So the size increase, they become hydrophobic actually. So they shrink, and when they shrink, you see it in the last picture, they occupy much less space. So they provide open space inside the gel, like interconnected open space, and they increase the permeability of the gel because they are like the mesh size of the gel kind of increase in this way.
What material is it?
It's metacryloyl, isopropyl acrylamide, because it was like another PhD project from polymer laboratory, so now I'm not so specialist in this case because I'm not.
Like epoxy? Goes it in the direction of
Epoxy. I'm not so specialist because it was, I'm not a chemist too, so that's why. It was like, as I told, the part of nanoparticles is from like the other project from polymer laboratory that they are like doing polymer particles.
Is there any potential other application except from this cartilage where you can use a release through
the idea
mechanical motion and heating?
It's a release for drug in mostly load-bearing tissues, which are connecting tissue. It can be tendon. We also are developing for nucleus pulposus. So for all joints that you have kind of load, there is almost no kind of drug delivery system because, as I told, the loading condition there, material they cannot stand there a lot, and that's why we targeted like load-bearing joints normally, like cartilage, nucleus pulposus, or tendon.
Do you have any idea of how efficient this energy conversion is like? You're converting mechanical energy into heat.
Yeah.
How is it? What fraction of that?
So that's
energy, goes into heat actually.
Yeah, that was the work that it was like the most challenge for this hydrogel, that you should play with the structure. As I told, we have to use very low, like cross-linker that provides high friction, and in this case we had like the damping ratio that we say that the coefficient that it's a ratio of dissipated heat, is dissipated energy, or the total input energy in this gel is 0.8, means that 80% of energy.
0.8, it's very high.
Yeah, it's very high. And
that's extremely high.
Yeah.
Oh, that's excellent. Do all the football players in South America know about this technique? Maybe they should advertise it more. Yeah. Any more questions? If
that's
this is
why
not
after this proof of concept,
no, I have
received like many like media.
I mean that press release that you showed, that was very impressive. So it must have impressed people in many places anyway. Anyway, thank you very much for this interesting contribution. We have a coffee break now, I understand, for half an hour. We are just about in time, and we reconvene at 5 o'clock, please, in the same room, same place. Thank you very much. Thank you.
And just a quick announcement. So if the speakers for the follow-up session are in the audience already, I request you to go to Nairobi and load your presentation beforehand. So Nairobi is a room next door, and if you're here, we can just walk there together.